What is union find? In computer science, a disjoint set data structure, also called union find data structure or merge find set, is a data structure that stores a collection of disjoint, non-overlapping sets. Equivalently, it stores a partition of a set into disjoint sets. Do you understand why I want to make this union find video now? Because the definition of union find is kind of complicated, but don't worry, we'll go through this together. Here's an example of disjoint set data structure. As you can see in each of the array, the elements only exist in that array. So if A is in the first array, it won't exist in array 2 or 3 or 4. This is a disjoint set. A graph can be also considered a disjoint set. So in this graph, you can see there are 3 distinct components. The union find algorithm is an algorithm that helps to identify and maintain this disjoint set. Imagine you're only given an adjacency list. An adjacency list is where you have a dictionary and each key stores an array of its neighbors. So key 1 stores 2 and 3, means that node 1 can go to 2 and 3. Similarly, key 4 stores 3, because 4 can only go to 3. So given this adjacency list, you want to find out how many islands are there. The union find algorithm will help you find out if there are 3 islands or they're actually all connected. There are 3 functions in the union find algorithm. The first is make set, second is find, and finally there's union. The make set operation adds a new element into a new set containing only the new element, and the new set is added to the data structure. Imagine a connected graph is represented by a set with all the connected nodes. So this graph would be a set of 1, 2, 3, 4. However, when you first start with just the node 1 and make a new set, the new set only contains 1 and 1 itself. That's what make set does. It contains only the node itself because we haven't explored the other nodes yet. The next function we have is find. Find finds the root of the tree containing x. The find operation follows the chain of parent pointers from a specific queried node x until it reaches a root element. This root element represents the set to which x belongs and may be x itself. Find returns the root element it reaches. The find operation basically returns what's the root of the tree that the node is a part of. For example, if you call find 3, we take a look, okay, 3, we go to its parent, alright, parent is the root, and so the root is 8, we return 8. If we call find 4, okay, we see start at 4, 4 go up a level, we see the parent is 8, we return 8. We call find 8, we see that 8 is the parent of itself, so we return 8. In the previous example that we have here, right, say we start with 1, but we explore 2 and 3. And then we call find 2. Then find 2, we look up to its parents, we see that it's 1. 1 is the root of itself, so we return 1. Finally, we have the union function. You call the union function on node x and node y. What it will do is that it will merge the 2 trees containing x and y. The algorithm works something like this. First, you find the root of x by calling find x. Next, you find the root of y by calling find y. And then you will merge the tree. How do you merge the tree? Here's what you do, right? You check if root x equals to root y. If they're the same root, that means they're already the same tree, you don't have to do anything. Otherwise, you make root y the child of root x, essentially merging the 2 trees. Or you can make root x the child of root y. Here's an example. Say we called union 3 and 5, right? So find 3, we find that the root is 8. Then we call find 5, we find that the root is 7. What do? Since these are not the same, it means that they're 2 different trees. So we're going to make 8 a child of 7, thus merging the 2 trees. So what determines that 8 will become a child of 7 and not the reverse? This is determined by the rank of the tree. Over here, the tree with the root 8 has a smaller rank than the tree with root 7. Well, you can't see it here, but just imagine that, okay? How this works is that when the 2 trees have equal rank, we just randomly pick one. So imagine 2 nodes, they just been initialized. In this case, both rank are 0, we just randomly pick one. If one tree has a greater rank, it probably means that tree is bigger. In this case, we want to attach the smaller tree to the bigger tree. This way, the search time from the leaf to the root will be smaller. If we attach the bigger tree to the small tree, we're just going to build a very disproportionate tree, where the leaf from the bigger tree reaching the smaller tree will be a lot longer. I'll explain this in more detail in the example section. Now that you know all three functions, it's time to put it together and show you how union find identifies and maintains disjointed set or disjointed graphs. Let's get started. The union function is really at the center of everything. What we're doing essentially is that we're provided with something like an adjacency list where we know the relationship between nodes. So we know that 1 is related to 2 and 1 is related to 3. We will call union on 1, 2, 1, 3 until we get ourselves a little tree that looks something like this. Imagine 1 being the root because we started with 1, 2 connected to 1, and 3 connected to 1. Imagine we have a graph like this, right, where we call the union function over and over again, but our adjacency graph might not be in order, so we might call union here, then union here, then union here, union here. Eventually we will get multiple trees. So imagine if we found 2 trees so far, 1 over here and 1 over here, and we're going through a relationship of 3 to 5, right? That's what's happening over in the union function where we join 2 different trees together. And that's how we find out that, this set and this set is actually connected. And finally, maybe there's a third tree somewhere over here, and we check that, hey, this tree and this tree has a connection over here. We call the union function and we connect them. And we find out that all of these 3 trees are connected, part of the same graph. When we finish calling the union function on every single relationship, we will be able to find out how many distinct sets are there. The number of distinct trees is the number of distinct sets. So over here, since there are 3 distinct trees, there's 3 distinct islands. Now it's time to talk about runtime. The runtime of make set is 01. We're just initializing a set with a single element in it. We won't be doing it every single time. We'll just be doing it when we first start to explore an element and we haven't explored any of its relationship yet. So if we are initializing n nodes, it will be O(n). However, if we do need to initialize n nodes, it probably means we have n islands, since none of them are connected to each other. Either way, make set will not be our bottleneck for runtime here. The runtime of the find function is log n with no compression technique. As we mentioned, we have a tree and we want to find the root. The worst case scenario, we start with the leaf. From the leaf, we want to reach the root, the runtime will be log n. Just a quick review on traversal from the leaf to the root in a tree. If we have a binary tree, it's log base 2, ternary tree, log base 3, canary tree, we have log base k. There are 2 compression techniques. Path splitting replaces every parent pointer on that path by a pointer to the node's grandparent. However, we can actually make the runtime a little bit faster by using compression techniques. There are 2 compression techniques. The first is path splitting, which replaces every parent pointer on that path by a pointer to the node's grandparent. The other compression technique is called path halving, which works similarly but replaces only every other parent pointer. The compression technique achieves the flattening of the tree. So imagine before compression we have something like this. This is horrible because if we say find x, it would take 1, 2, 3 steps. After the compression technique, the tree will look something like this, very flat. So now if we call find x, it will only take 1 step. Each time we call find on a node, we will compress the tree a little by little. This is why when we first call find on x, the runtime will be log n, right? But the second time when we call find x, the runtime will only be O1 because there's only 1 step from x to the root after the compression. The difference between the 2 exists on this line, right? So immediately over here, x becomes x parent, x becomes x grandparent, whereas here, x parent first becomes x grandparent, and x then also becomes x grandparent. Let's look at the following example. Say we have 1 to 2, 2 to 3, 3 to 4, 4 to 5. For path splitting, before x is 1, parent is 2, grandparent is 3, right? Since we assign x to becomes x parents, x is now 2. Similarly, we assign x parent and equals x grandparent, x parent equals to 3, because we're doing this simultaneously. However, over here, what we're doing is that we are first assigning x parent equals x grandparent. So x parent equals to 3. Immediately, we're assigning x equals to x parent, which means that it is also 3. I couldn't find any research telling me which one is faster, however I did find a diagram that represents the two, path halving and path splitting. If you're interested, I'll also include the link below for you to explore the original article. Either way, the compression technique will help us to achieve a runtime of blah 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 n or alpha n. In this case, the blah 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 n or alpha n is the inverse Ackermann function. Similarly, I'll include the article in the link if you are interested. What is important to note here is that the Ackermann function is a lot less than log n. That's what you need to remember. Finally, we have the union function. The majority of the runtime goes to calling find twice. This means that the runtime of the union function is also the Ackermann function n. Therefore, the runtime of running n union find function would be n times Ackermann function, which is smaller than n times log n. Alright, it's time to talk about the elephant in the room. There's another algorithm that can help you find disjoint set, especially finding islands of graphs, and that is DFS. If you're familiar with DFS, you will know that the runtime of DFS is O(n). It only visits each node once, but the runtime of union find is n Ackermann function n, which means that union find is slower than DFS. So why would you use union find instead of DFS? Well, in this video, you have heard me talk about union find as an algorithm and as a data structure. This is because union find is a data structure, and what that means is we can continue to add to union find. Imagine we have a graph like this, but this continues to grow and we have new nodes coming in live. For union find, we can continue to use our union find data structure to check if the incoming node is part of an existing graph or it's a separate island. On the other hand, DFS cannot handle dynamic content. What this means is that whenever a new relationship between two nodes come, you'll need to run DFS again and again. This is why you want to use DFS on static content and use union find on dynamic content. This is why union find is often used in autonomous vehicle, because the environment around the autonomous vehicle is constantly changing, and union find can handle dynamic content, whereas DFS you have to run it every single time. Alright, let's try it out with an example. Number of operations to make network connected. There are n computers numbered from 0 to n-1 connected by Ethernet cable connections. Forming a network where connections I equals AB represents a connection between computer A and B. Any computer can reach any other computer directly or indirectly through the network. You're given an initial computer network connections. You can extract certain cables between two directly connected computers and place them between any pair of disconnected computers to make them directly connected. So basically you can yank any cables and connect to other computers. Return the minimum number of times you need to do this in order to make all the computers connected. If that's not possible, return -1. The diagram explains it quite well. So basically you have 0, 1, 2 connected by a couple of cables, and then we have 3 that's not being connected. So we yank this cable and connected 1 to 3 over here, and now everything is connected. The number of cables we needed to yank is only 1, so we return 1. Here is another example. We see that 0 is connected to 1, 1 is connected to 2, 0 is connected to 3, and we have these computer 4 and 5 which are not connected. So we yank these two cables, connect 1 with 4, 4 with 5, and now everything is connected in a single network. To translate the confusing question description into computer science language, we basically have connections which represents a bunch of relationships. We want to use these relationships to find out how many isolated sets are there. The number of cables we need is the number of isolated sets minus 1. For example, we have 1, 2, 3, so we only need 3 minus 1, 2 cables. A cable over here and a cable over here. This begins to sound like a problem where you can solve using union find. Union find will help us maintain distinct sets. In this case, after we run union find with every single relationship, we can check how many distinct sets are there and return the number of distinct sets minus 1. However, there's an exception. As you can see here, we can actually run out of cables. We have 6 computers, but we only have 4 cables. That is not enough cables. We need at least 1 cable per 2 computer. So that means we need n-1 cables. Here we have 0, 1, 2, 3, 4, 5. 6 computers. In this case, we need at least 5 cables. So 1, 2, 3, 4, 5. Let's take a look at the actual code. MakeConnected is the main function where we take n, the number of computers, connections, the array of relationships. If connections is less than n-1, it means that we don't have enough cables. We return -1. Otherwise, we initialize our union find data structure. Then, for each pair of connections, we run union find on the 2 nodes. Finally, we return the results. What we're trying to do here is we're trying to find how many islands there are. To do this, we find the number of disjoint sets. Each disjoint set in the union find data structure is represented by itself being the root of the tree. So for each number up until n, so 0, 1, 2, 3, 4, 5, 6, blah, 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 so for each and every single node, we check if it's its own parent. If it is own parent, it represents the root of a tree. So we count the number of roots, which is the number of trees, representing the number of disconnected islands. And we return that number -1 as our result. First, we initialize our union find data structure with a dictionary of ranks and dictionary of parents. Here, the key to ranks is the node itself. The key to parents is also the node itself. The value of rank is the rank number. The value of parents is the parent of the node. Next, we can see that we have a makeSet function. This is quite simple. MakeSet is called when we just initialize the node. So the parent of that node is itself, because that's the only node in that tree. We also initialize the rank to be 0 since we haven't merged with any other tree yet. For the find function, we take in the node x. We first check if x is in parents or not. If not, we gotta initialize it by calling makeSet. Next, we're gonna traverse upwards to find the root of that node. While the parent of the node is not itself, we use path compression and continue traveling upward all the way until the parent of the node is itself. In that case, we return the parent. This function was a little bit confusing when I was learning it myself, so I'll explain it in a little bit more detail. What we're doing here is that on each iteration, we are assigning a self to the parent. The later half of this is the compression part. Just remember we're assigning ourselves to the parent. That is how we're constantly moving upward by a level. This exit condition is to check if, hey, our current pointer's parent is a self. Why do we know this is an exit condition? This is because we initialize it as the node to become the parent of itself. So when we reach this, we know that we are at the root. I hope you can appreciate this diagram a little bit more because it shows this. So first we start at 3. Alright, 3 is not its parent, so we go up. Next, we check if 8 is its parent. Since 8 is its parent, we know that 8 is the root. Finally, we have our union function. We find parent of A and parent of B. If the parents are equal, we return because they are the same tree. The next part is a little bit confusing, so I'll explain the concept first. We want to attach the smaller tree to the bigger tree, but how do we find out which tree is bigger? How we find that out is by comparing its rank. If a tree has a bigger rank, it means that the tree is bigger. If 2 trees have equal rank, we might as well pick tree A because we're just picking at random, right? Alright, next, when we assign the smaller tree to the bigger tree, we should bump up the rank of the bigger tree. This way, we can always identify which tree has a bigger rank. That's the basic concept. To shorten all that logic into code, what we're doing is first comparing the rank of A and rank of B. If A is smaller in rank, we swap the two. This guarantees that A will always have the biggest rank. Next, we bump up the rank of A by 1. This is because we're going to merge a smaller tree into A. How are we merging that tree? Well, we're going to assign the parent of the smaller tree to the bigger tree. So we're assigning parent of B, the smaller tree, to be A, the bigger tree. As you can see, this is not the fastest algorithm. However, it does the job. I hope this helped you to realize why this is sometimes called a data structure and other times called an algorithm. Yes, it's an algorithm because it contains algorithm parts and functions. However, it's a data structure because we use it as a data structure. We can continuously input relationship into the union find and maintain our disjoint set. Next, I'm going to show you some examples how this long code can be shortened when you actually want to use it in a question. What we're doing here is that instead of creating a separate class for union find, we're extracting all the functionality, putting most of it in a for loop, and calling it a day. First, we still need to check if the number of connections or relations is less than n-1. If that's the case, we don't have enough cables to maintain the network, we return -1. Similar to how we initialize the union find, we first create parents and we create number of ranks. However, here we're immediately initializing them. We initialize all the rank for each of the node to be 0, and we initialize all the parent of each of the node to itself. Over here, what we're doing is that for each connection, A, I, and J, we're basically running union function. So first, we want to find the parent of I by continuously traversing upward. Next, we find parent of J by continuously traveling upward. If I equals to J, it means they're the same tree. We continue. Otherwise, we check if the rank I is smaller than J. If it's not, we reverse the two. This guarantees that I will have the greater rank. Next, we bump up the rank of I, the bigger tree, by 1. And then we attach J, the smaller tree, into the bigger tree. This should be very familiar to you as it's basically exactly copy by copy what we're doing in the union function. Finally, we want to get our results. We want to find the number of distinct sets, or the number of islets. So for each computer, I in range n, 0, 1, 2, 3, 4, 5, 6, blah 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 until n, we check, hey, is the parent equal to itself? If it is, we increase our number of island count, or number of distinct set count. Finally, we return the number of islands -1 as the number of cable we need to make everything connected. Just to clarify, this is the number of links we needed to change. And let's take a look at the runtime. As you can see, this is way faster. Reason being is that we didn't need to create a separate class. What's more important is how slow the algorithm can be if you remove the optimization with rank. So over here, we remove our bumping up of rank. So every single tree will have rank 0, and we only beat 13%. If you can remember, even the version with another class beat 33%. So removing the rank optimization slows down this algorithm dramatically. Alright, this has been everything you need to know about union find. Hope you enjoyed. I definitely learned a lot. I didn't really understand what's the difference between using union find or between DFS, or like why we need to use union find. I was also unfamiliar with the runtime of union find, but definitely learned a lot through this experience. So hopefully this video helped you as well. As I said before, these videos serve more like a study note for me, and I genuinely enjoy making it because I feel like each time I invest time into a topic, I learn a lot about it, and once I produce a video, the idea gets drilled in my mind and it's irreplaceable. Anyways, see you next time. If you like the video, subscribe. If not, that's alright. Bye!